Hello, welcome to another episode of our series on how to use GeoGebra in teaching our students, specifically in mathematics and statistics related topics. In this particular presentation, I'm going to show you how we can use another view of GeoGebra, which is called the probability calculator. I will give you a tour about this view, and also I will be showing some problems that can be answered and can be explained using this particular view of GeoGebra. So stick with me and follow through. So let's go ahead and open our GeoGebra software. So first, I'm going to show you where we can access this view. Actually, if you open GeoGebra, it will automatically give you the option at the right part here. So we can see the different views. We have the 2D graphing, or the 2D graphics. We have geometry. We are also done with the 3D graphics. So we want today, or in this presentation, the probability view of GeoGebra. So we can click here and it will automatically put us in our probability view. So actually in this view there are two main tabs. We can see here that we have distribution and statistics, although we will be focusing on the different distribution for this particular video. So just a tour in this view. Under distribution, we have here the different distributions. So if we click here, we can see the different options. We have the normal distribution, student for students, T distribution, we have the chi-square distribution, F distribution, exponential distribution. We have a lot of distributions here. We have the binomial, the Pascal, the Poisson, and hypergeometry. So anyway, there's a lot to tackle here, but I'm going to identify the most common and the most important. This will be the content of this presentation. So let's start with our normal distribution. If we set this one to normal distribution, what we see here is actually the graph. So this is what we mean by a normal distribution. So these are the graph, and we can see here two triangles here, triangles that we can change. We can slide, it can go to the left and to the right. And in statistics theory, we know that the area under the curve, so this is the distribution, but the area under the curve gives us the probability of a particular number x to be either less than or equal or greater than or in between two numbers. So what do I mean? Remember that for a normal distribution, we have two parameters. That is actually our population mean and the population standard deviation. This means that we can only build a normal distribution if we provide not necessarily the raw data, but the corresponding population mean and the population standard deviation. It will build us the normal distribution corresponding to those numbers. And what we can do here is to compute for the area under the curve. So we can actually specify what we are computing. If we are computing the probability that a particular number is between two numbers, like this one, what we see here is the probability value. This 0.6746 is the probability value of a number. If you draw it in this particular normal distribution, the probability that x is between 0.9917 and negative 0.9751, we can see here the boundaries, the probability of getting a number between these two numbers, given that the distribution of our data is normal, that is 0.6746. Suppose we want to identify the probability that x when you randomly select a number x from our normal distribution, the probability that it is, we can specify a direction. Say the probability that x is, notice I click this button here, x is less than, say, I want it to be 1.5. So what is the probability of getting that? It will give us a probability value of 0.9332. So that is the area under the curve to the left of 1.5. So anyway, our mean is set to 0. That's by default the number or the value of our mean, and the default value for our standard deviation is 1. So again, in statistics, if these are the numbers or these are the values for our mean and standard deviation, we call this specifically as our standard normal distribution. But we can of course change the values with this one. So if we change this one, say we change it to 90 and we change our standard deviation to say 5, then this is not anymore the standard normal distribution, but just a normal distribution. I will be showing you some problems that can be answered by this particular view of GeoGebra. Here is our first problem related to a normal distribution. Again, normal distribution is a continuous random variable x having a bell-shaped distribution that is so evident in our graph. So whatever mean and standard deviation we choose, it's still a bell-shaped distribution. The parameters, as I mentioned a while back, it's the population mean and the population standard deviation. Here is an example of a problem that we can answer using this particular view. We have here a problem. Let me read this first. The scores of students in a math test is normally distributed with mean 90 and variance 36. Remember that what's given here is the variance. There are two problems. The first one, if 74 is a failing score, what is the probability that a student will fail? Or what is the probability that the score is 74, exactly 74, or less than 74? And the second one, what is the probability that a student's score is between two numbers, 80 and 100? Equivalently, the questions are, what is the probability that x is less than or equal to 74? If we write the first problem, mathematically this is how we write it. We are looking for the probability that when we draw a number from that distribution, from this specified distribution in the problem, what is the probability that it is less than or equal to 74? And of course, the second question is mathematically equivalent to the probability that x is less than or equal to 100 and greater than or equal to 80. Again, the parameters here are the mean and the standard deviation. The standard deviation is 6 based from the given value of the variance. Remember that the standard deviation is the square root of the variance. Since the variance is 36, it follows that our standard deviation is 6. So how do we answer this problem using GeoGebra? It's really easy. So we need to specify the parameters first. I think we got 90 in our GeoGebra, so we do not want to change this one. But for the standard deviation, we're going to change it with 6. And then we change the values here. We are looking for the probability that x is less than or equal to 74. We are on the correct button. It's this button, but we have to change 1.5 to 74, and it automatically gives us the probability. So this is the probability that a student will fail. It's really a small number. It's almost equal to 0. So we are done with the first problem. We can answer this problem now. That the probability that a student will fail given the information on the distribution of our dataset, it's pretty slim. Second question, what is the probability that it is between 100 and 80? So we have the same values for our parameters, except that we have to change what we are computing for. It's between two numbers. We click this middle button here because it's an interval, and then we change. X should be less than or equal to 100 as was mentioned in the problem, and it should be greater than or equal to 80. And we see the corresponding area here. The area here is equal to 0.9044. How else can we use this problem? Actually, for problems like this, we are given the number of examinees, the number n. So say there are 1,000 students. We haven't included it here, but it is possible. Using these probabilities, we can actually compute how many students would fail. So a while back, it's like 0.0030 plus. If we want the number of students that will fail, we simply multiply that probability to 1,000. If we do that, multiply the probability of having an x value that is less than or equal to 74. A while back, we computed this one as 0.0038. We multiply this one with the number of examinees. Say it's 1,000. The value here is 3.8 if we round this one because we are referring to the number of examinees. We have like 4 examinees that would likely fail if we set our failing score to 74 or below. So that's the number of failing students. How many students would get a score between 100 and 80? Since the probability is 0.9044 and there are 1,000 test takers, we simply multiply this probability to 1,000. So we might have a number like 904. So the probability is really high. This is our normal distribution. There are other distributions, of course. For example, we have, let's have the binomial distribution as our next distribution. Remember that a binomial distribution is a discrete distribution. That's why it looks like this. The parameters here are n and p, and the buttons here are very similar with the normal distribution. Before we can use this one, we have to recall what we mean by a binomial distribution. What is a binomial distribution? First, we need to know what we mean by a binomial experiment. And in statistics, a binomial experiment is one that possesses the following properties. Number one, the experiment consists of n trials. So you have an experiment. What are examples of experiments? We have the classic ones like tossing a coin. If you toss a coin 10 times, the experiment there is tossing a coin and the number of trials is 10. For a binomial distribution, each trial result is an outcome that may be classified as a success or a failure. So in your experiment, when we need to specify which is what we mean by a success and what we mean by a failure. So we can set having a head when we toss a coin as your success, and the other way around, meaning obtaining a tail, that is how we define a failure, or it's the other way around. So that would depend on how you define what we mean by a success. Number 3, the third property for a binomial distribution, the probability of success, we denote that by P, remains constant from trial to trial. And then the repeated trials are independent. So each tossing of coin, it doesn't really affect the outcome of the other trials, meaning the next toss of the coin. The parameters for a binomial distribution are n and p. N is the number of trials and p is the probability of a success. So you get one trial and then compute for the probability of the success. This is a basic concept in probability. So how do we compute P? We need to know the number or the number of elements that are contained in our sample space, and then the number that that event will occur. Let's have here an example. Let's stick with tossing of a coin. What is the probability of obtaining at most 10 heads if the coin is tossed 20 times? So the experiment is tossing a coin, and let us define that the success that we want here is having a head, because the problem involves obtaining heads. Let's identify first the parameters. It's of course 20, that's very obvious. And the probability of success, what is success in this particular problem? Obtaining a head. So in each trial there are only two outcomes, because you have only two sides of the coins. That's either obtaining a head or obtaining a tail. And for our two outcomes, we only have one event that a head will be obtained. So the probability is 1 out of 2. The question really is, what is the probability that x is less than or equal to 10? Now, how do we know that the proper inequality that we should use is less than or equal? It's because it's mentioned in the problem that the probability of obtaining at most, when we say at most, that is the ceiling number. So it could be 10 or less than 10. It could be 10, 9, 8, and so on. So it could be 0. Let us compute for this one. So since our problem involves the probability distribution, we use the probability distribution of GeoGebra. So let us remember our parameters 20 and 0.5. Those are the numbers that we need. So we have 20 and 0.5. It's already here. The probability that we want to compute is the probability that x is less than or equal to, what is that, 10. Do we have another example for a probability distribution? Let's check. I think we have. Our example number 2 involves a different experiment now. So we have a die. We are tossing a die, not anymore a coin. We're going to toss that die. Remember, die is an object with 6 faces. For each face, we have the numbers 1 through 6. What is the probability of obtaining, letter A, at least 3 twos, and letter B, exactly 3 twos? So why is this a problem involving binomial distribution? Because we can categorize the outcome of a trial or an experiment with a success or a failure. So we can set having 2 when we toss that die as our success, and the other numbers like 1, 3, 4, 5, and 6 as the definition of failure. So if we have those numbers except 2, then we failed achieving what we want in our experiment. Parameters are, it's very obvious here, it's very clear that we are going to toss it 5 times. That's the value of n. And for each trial, what is the probability of success? Obtaining a 2. Since there are 6 numbers, so there are 6 possible outcomes for each trial, and for those 6 outcomes, there's only 1, 2 that will happen there, that could possibly happen. So the probability of a success for a trial is 1 out of 6. That should be the value of our P, 1 over 6. Let us mathematically write the problem so it would be easier for us to compute for the corresponding probabilities. So what's letter A? It's at least 3 twos. When we say at least, the least number of 2 that we could have is 3. So it could be more than 3. It could be 4. It could be 5. That means that when we toss that die 5 trials, we have 5 twos. So that is how we write the first problem. It's greater than or equal to 3. Remember the word at least. And then of course the second problem is exactly 3, so the probability that x is exactly 3. Alright, let's answer letter A using GeoGebra. So the number of trials now is 5, and the probability for a success is 1 out of 6. So 1 over 6. We are concerned with computing the probability that x is greater than a particular number. So I will click this button here, the rightmost button, right-sided. It says x is greater than or equal to 3. And there we have it, the probability corresponding to that question. So that's 0.0355, probability that x is greater than or equal to 3. How do we answer the second problem? If we investigate our options here, is left-sided or right-sided or in between. It doesn't directly give us a way to compute for when x is exactly equal to a particular number. But we can use the middle button. So if it's exactly equal to 3, we can just make the right side and the left side values the same. X is greater than or equal to 3. At the same time, it's also greater than or equal to 3. This means that x is exactly equal to 3. And the probability is 0.0322. It's almost the same value as we computed a while back, but it's just different in the third to fourth decimal values. Alright, so that's an example of a problem where we can use the binomial distribution. Let's proceed to another problem. We have here a hypergeometric distribution. We first look at how we define a hypergeometric experiment, because it's a bit different with a binomial experiment. A hypergeometric experiment is one that possesses the following properties. Number 1, a random sample of size n is selected from a population of size n. I have prepared here a visual that would help us imagine what we mean by the different properties. So imagine that this box here, this is the size of our population. So this is of size n. And from our population, we're going to identify a sample of size small n. What is the second property? K of the n items. So there are n items. We identify some part of it, that's k, and we classify it as the definition of successes. And n minus k will be classified as failures. So n minus k simply means the rest of n when we subtract k. We see that the parameters here are 3. There are 3 parameters. We have the population size, the sample size, and the number of successes. K here is associated with our population. Always remember that. So to give you an idea of an experiment that would integrate our hypergeometric distribution, let's have this one. A committee of size 5 is to be selected from 20 people. Of those 20 people, 12 are female and the rest are male, meaning there are 8 males from our population. Now we want to form a committee of size 5. So it is possible that those 5 are all male or are all female or a combination of male and female. So that is our sample size. The question is, what is the probability that at least 2 of those 5 individuals that we will be identifying from the population, at least 2 of them are female? At least 2 of them will be included in our 5 size group. So how should we solve this one? Let's identify the parameters. Our population size is 20. We divide it by 12 and 7 because it mentioned here that there are 12 female, and we're going to define success as having a female because that's what is asked in the problem. So we set this one as, actually there should be 8 not 7. So let us correct this one. Yeah, these are the parameters that we need. Some population size equal to 20, n equal to 5, and k equal to 12. So remember those figures, and let's compute for the probability. Again, the mathematical equivalent of our problem is that the probability of x is greater than or equal to 2, because the keyword here that we use is at least. So x could be equal to 2 or 3 or 4 or 5. Of course, we stop with 5 because there should be only 5 people in our group. Alright, so 25 and 12. Let's look for our hypergeometric distribution. It's the last one. And then we input our parameters. It's 20. And then 5. And then the value of k. It says here it's sample, but this is actually the value of k. So we set this one as 12. We are computing for a probability, the probability that x is greater than or equal to 2. So we're going to make use of the right side button here. X is greater than or equal to not 4 but 2. And there we have it. The probability for this problem is 0.9422. It's really high. So it's likely that we will be able to choose at least 2 female when we have 20 people in a group. At the same time, 12 of them are female. So that is very understandable and logical because there are more female in the population. So there's more chance of including a female in our group. Alright, let's have the last distribution. It's called the Poisson Distribution. These are one of the most important distributions in statistics. Just a brief description of what a Poisson distribution is. It is a distribution that gives the number of outcomes occurring during a given time interval or a specified region. So our keywords here are during a given interval or specified region. So this distribution is more applicable for experiments where we count the number of events in a particular interval of time or a particular region, and we want, based from the data, we want to compute for the probability that an event will occur. There's only one parameter for this distribution. We only need the population mean. Let me give you an example so we can visualize this distribution more. Last year, the average number of days that classes were suspended is 10 days. What is the probability that classes this year will be suspended for 15 days? So based from a previous data, so we counted or we computed the average number of days that classes were suspended last year, and that's 10. We want to compute the probability that the average number of suspensions that will happen this year is 15. So that's what we want. And again, we only need one parameter, the population mean, which is given in the problem, that's 10. Mathematically, the problem is the probability that x is exactly equal to 15. It's not less than, it's not greater than, but it's exactly 15. So let's go ahead and do that in our GeoGebra. So let's look for the Poisson. It's the second to the last distribution, and then we input our population mean, which is 10. What we want to compute is the probability that x is exactly equal to 15. So again, we use the middle button to do that. So we simply make the right and the left values here the same, 15. Alright, so what is the probability? It's really small. It's 0.0347. So this is the chance that the number of suspension this year is 0.03. So that is a Poisson distribution. Of course, there are lots of problems that can be answered using our different distributions. In fact, I only presented here applications of our four distributions, but we can explore more with the other distributions. So I guess I will end our presentation here. I will see you in the next video for a presentation on the other tab for this view. So remember, we have another tab here. It's called Statistics. Let us explore this one in the next. I will see you then.